take a look at what an integral actually means graphically today and tomorrow. And we were doing fantastic yesterday by actually finding antiderivatives, like the algebraic way to solve an integral, or at least start to solve an integral. But now we're going to take a look at a graphical approach. Okay, what does it mean in terms of a picture? So to kind of recap certain characteristics about a graph that we've already talked about this year, let's say we have maybe a general parabola shape. We're going to call this an f of x function. This year, we've spent a lot of time talking about, let's see, I'm going to do f of a. I'm going to say this point right here is a. All right, if I had an equation, okay, which I don't here because I have a graph, but if I had an equation and I plugged in a into that equation, what would that tell me about the graph of f of x at a? What does an original function represent? Position, a height in this case, a value, a y value. Okay, so y value of f of x. Okay, a position or a point on a graph. What if I were to plug in a into the derivative equation? What does that tell you about f of x? Slope. Okay, slope of f of x at that spot. What if I plugged in a into the second derivative? What does that tell you about f of x?
Concavity.
Concavity, we're good. Okay, concavity of f of x. So notice how depending on which function we want to evaluate, it's going to tell us something different about this f of x graph. What we're going to lead into is an integral. Now, for an integral, you don't plug in one number per se. For an integral, we're actually going to have two values. And those two values are typically written at the bottom and top of that long curly S. And these numbers that are going to be there are representing an interval. So we're going to go from this point of A to maybe a second point at B. And what's a little bit different, because it's new to us, we haven't really seen integrals before, is there must be another characteristic about this graph of f of x that we can evaluate. So there's something else going on here that we can look at instead of just a point, instead of just a slope, instead of just the concavity or the curvature. For those of you that have physics, this might make sense, or you've seen this before. What does an integral represent graphically? Yeah? The area under the curve. So if I were to go from A to B, and I'm going to shade in all of this, okay, that's what an integral is going to help us solve or compute. So this is the area under the f of x function. Okay, specifically to the x-axis. So we're adding on yet another characteristic of a graph that we can start to analyze. We've done points, we've done slopes, we've done concavity. Now we're going to look at area underneath. And we're eventually going to get to what this value actually means, like in terms of maybe that particle motion or just functions in general. But for now, I just want to practice calculating it. Okay, can we get this result? To help us calculate it, it would be nice if we can use some geometric shapes, because we know areas of rectangles, areas of triangles, areas of circles, okay? But notice how underneath this parabola, it's not a solid shape, for instance. Like, this is not a perfect semicircle, you know what I mean? Like, we can't calculate the area exactly using some shapes, at least for this graph. So that's why we're going to talk about some estimates. And they're typically called, let's see, they're at the top, Riemann sums. So a German mathematician, Riemann, yeah.
What happens if you have a positive or a negative parabola? It's still the space from things to the x-axis, right?
The x-axis. So it would be It'd be all of that. Sounds good? Okay. So these approximations that we're going to talk about today and tomorrow are called Riemann sums. They're from a German mathematician called Riemann. I forget his first name, but he's the one that basically developed this approach to help us use triangles, trapezoids, shapes that we're familiar with to help us approximate an error under a curve. We'll eventually get to how we can find the area exactly, okay, using some calculus, but for now it's going to feel like a throwback to geometry because we're going to be using area formulas. So not much calculus is going to be involved with this. Okay, so the first type of approximation that we're going to look at is what's called a left-hand Riemann sum. And left-handed is typically signifying some type of rectangle that we're going to draw within this area. They also tell us that we want a length of 2. We'll talk about that in a moment. So as a visual, as an example, notice how we have this upside down parabola. They give us the function at the top. And we want to subdivide the interval from 1 to 7. So from 1 to 7, we're basically looking at the area under the curve in that section. And we're going to use rectangles to help us estimate what that area is. So if we're going from 1 to 7, okay, and we want rectangles to have a length or like a distance of 2, how many rectangles are we going to be able to fit in that interval? Can we figure it out? 3. Okay, we'd go from 1 to 3, 3 to 5, and then 5 to 7. Okay, so section off your intervals of where these rectangles can be drawn. All right, so this is how we're going to draw a left-handed Riemann sum. Our first rectangle is going to go from 1 to 3. Notice how the left-hand side would be at the x value of 1. So on the left-hand side, I want you to draw up until you hit the curve. I want you to make kind of a big dot at that spot. You're going to go perpendicular to the right-hand side and then back down to 3. Okay, so there's a rectangle that's 2 units wide or 2 units long, and notice how the left endpoint, the left vertex of that rectangle is hitting the curve. Okay, that's why it's called a left-handed Riemann sum. Okay, we're going to repeat the process for the other 2. So this next rectangle is going to go from 3 to 5. We're going to draw up on the left-hand side of 3 until we hit the curve. Okay, make your dot. Go to the right and then back down. All right, and the next one, we'll trace up from 5 until you hit the curve. Go to the right and back down. Okay, so it might be a little difficult at first because they are overlapping each other where they share a side, but notice how the vertex of one rectangle might be different from the vertex of another. Okay, so draw each one individually. Are we okay with that drawing? We understand where that's coming from? Okay, so these 3 rectangles we're going to use to help us figure out the area under this curve from 1 to 7. So in terms of notation, if we're going to do the area under a curve, that's going to be an integral of this function f of x. Okay, we're going to have the dx on the end. What numbers are we going to use for the bottom and the top of that long s? What's the interval that we're using? Where do our rectangles start? Where does the last rectangle end? 1 to 7. Yep, good. Okay, so the area under the curve from 1 to 7 is approximately. Okay, we're going to have to use the squiggle squiggle. So to approximate the area, we're going to figure out the area of each individual rectangle, and then we can add them up. Okay, so how do we find the area of a rectangle? Length times width, base times height. Okay, so this first rectangle has a base of 2, okay, because we went from 1 to 3 on the x-axis. How can we figure out the height of the rectangle? How tall is it? Yeah? Okay, like we said over here, I'm going to flip it, okay? If we plug something in to an original function, that's representing a y value, aka a height of a graph. Now, graphically, it kind of seems like it should be around 7, but we don't know what that is exactly. So we're going to take f of 1. Now, on our calculator, I'm going to show you how to do this fairly quickly. I want you to go to y equals, type in the function, we'll make the window the same as what's on our paper. So we go from -1 to 9 on the x-axis, and looks like the same for the y. All right, so there's our curve. If you hit the trace button and immediately type the number 1, notice how it'll select it or choose it as an x value, and you can hit enter and it will give you your ultimate y value in the end. Okay, so f of 1 is 6.666667. Okay, I know you might feel obligated to round to 4 decimal places, but you don't round until your final answer. So if you have to use decimals to help you get your final answer, make sure you use like 5 or 6. Okay, don't round to 4 until the very end. Okay, so we'll come back to that in a moment. So this is going to be the area of our first rectangle. We now have to add the area of the next rectangle. Notice how the middle one also had a base of 2. And how can we find the height of the middle rectangle? What number can we plug into our function? Yeah? 3. Okay, notice how that's coming from the left endpoint that you made that big circle for. Okay, so let's go ahead on here, we'll hit trace and then the number 3. Looks like we'll get 8. Bless you. All right, and then we'll add the last rectangle, again, base of 2. The height is going to come from the left endpoint that we drew, and that had an x value of 5. All right, so on our calculator, trace 5, we'll get another 6.66666. All right, so can you guys take a moment and actually calculate all that together? 2 times f of 1 plus 2 times 8 times, or sorry, plus 2 times f of 5. Can we get some value in the end? Any luck? 42 point 6 6 6 fourth decimal place 7. Okay, chop it 6, round to 7, either one. Okay, so there's our approximated area. Actually, maybe this should be a squiggle. Okay, approximately 42.6667. Now, can we take an educated guess as to whether this approximated area is over or below the actual area under the curve? Why?
Because there's more rectangle outside than inside.
The inside. Okay, so if you take a look at this first rectangle, all of the black I shaded is under the curve, but notice how we are not including this little sliver that we actually should be including. Okay, now for the other ones, this entire rectangle takes up the space under the curve, but here we're actually including value that we should not be including. And in the third rectangle, we have that same case. So if you look at the underage versus the overage, I guess, notice how we have more overage than underage. So I would definitely classify this as an overestimate. Okay, and we can see that graphically. How are we doing with our first Riemann sum? Pretty good? Okay, no calculus. It's just area calculation. Okay, we're going to amp it up a little bit. Okay, we're going to do another one, left-handed sum. It's the same function. It's the same graph, so you don't have to worry about changing your calculator. This time, we're going to use rectangles that are 1 unit wide, and we're going to be using the same interval. Okay, so let's go ahead and practice drawing our rectangles. If we want to have a 1 unit width, we're going to have to go from 1 to 2. The left-handed side is the side of 1. So I'm going to trace up that side, make my dot, go to the right, and then back down. Okay, repeat the process until you end at 7. All right, looks like we have 6 rectangles this time. All right, so in terms of notation, we're going to say the area under the f of x graph, so the integral of f of x dx from 1 to 7 is approximately all of the rectangle areas added together. Okay, so let's go ahead and write this out. The first rectangle, in terms of area, we need base times height. So base is 1. What can we use to help us find the height? F of 1. Okay, that's where the left endpoint came from in terms of the x location. So the next rectangle has another base of 1. The left endpoint came from f of 2. Okay, and then you're going to repeat the process until you get to the very last rectangle, base of 1, height, f of 6. Okay, now we already know, what did we have on the previous one? We already know what f of 1, f of 3, and f of 5 are because we wrote those down. Maybe we'll go ahead and write down f of 2, f of 4, and f of 6. Okay, those are new. So on your graph, we'll do trace 2, trace 4, trace 6. All right, can you calculate all of them and try to estimate the area under this curve? Any luck? $41.6, 6 or 7, okay? Chop it, round it, whatever you want to do. Over or under estimate? Over? Let's see. Okay, so this rectangle under, this rectangle slightly under, but it looks like the last 4 are definitely over. So when you look at kind of the total over or under, I think we have more over than under. Okay, so over estimate. Now, they were both over estimates, but do we think one is a better approximation than the other one?
This one's better.
Why?
It's closer to the actual. More exact.
How do you know it's more exact?
There's less overage and underage.
Okay, notice how the areas we shaded here, like for the over and under, are far less than what we shaded here. Okay, so it seems like we have a nice pattern going on here where the more rectangles we use, the better accuracy we have. Okay, so speaking of, let's try another one. This time we're going to use a half unit. So let's practice drawing in our rectangles. We're going from 1 to 7. If we want a half unit, we're going to have to go from 1 to 1.5. Trace up the left-hand side, make your dot, right and down. So these are going to be very thin. Okay, try to draw these accurately. All right, 1, 2, 3, 4, 5. My eyes are starting to cross. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 12. All right, we got to do 12 of them. So the area under the f of x curve from 1 to 7 is approximately. All right, so one rectangle at a time. Base was a half. And we're going to use the left endpoints to get the heights. So the first left endpoint came from the x value of 1. If we move to the second rectangle, it has another base of a half. Where did its left endpoint come from? 1.5. Okay. The third rectangle, base of a half, if its left endpoint came from 2. Okay, dot, 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 dot. The last rectangle, base of a half, height came from the left endpoint of 6.5. Okay, so I think from the previous 2 examples, we already know what the function values are at the whole numbers. So now you're going to have to plug in 1.5, 1 or 2.5, 3.5, 4.5, 5.5, and 6.5. Okay, you're going to have to use all those to help you out. Let's see, I'll check them out on here. Bless you. Am I okay in making the assumption that we can go from there with the calculation? Okay. Anybody with quick fingers?
I got 45.2083.
I think you're a little off. 916. I like that. Okay, so we can probably use the previous two as a gauge, like as to whether we're close or not. Notice how the first one was 42, and we said that one was an overestimate. The next one was 41. That was also an overestimate, but we said this one was better. So it shouldn't be more than 41.666. So I think this one makes sense. Okay, maybe double check it if you weren't able to get it, but you have the right numbers to work with. I know it's a lot to type in, but you have to make sure you're taking your time with your calculator. Over or under? How can you tell? It's very minimal, right? Because we have so many rectangles there, we're getting more accuracy. The ones on the right, though, are definitely little over corners if you take a moment to look at them. Okay, so again, I would say this is an overestimate, but probably not by much. Okay, how are we doing with left endpoints? Pretty good? Okay, let's try a few more. This time, let's switch it up and do a right-handed Riemann sum. So instead of doing a left endpoint, we're going to do a right endpoint. Thank you. All right, so we're going to start off easy. 2-unit intervals or widths of rectangles. It's still the same function. It's still from 1 to 7. Which means we can use all of those values that we had previously. Our first rectangle is going to go from 1 to 3. Now, since this is a right-handed Riemann sum, we're going to trace up the right side of this rectangle, make our dot, go to the left, and then back down. Next one we go from 3 to 5. Trace up 5, make your dot, go to the left. Last one, trace up 7, make your dot, go to the left. All right, so the area under the f of x graph from 1 to 7 is approximately, if we look at our first rectangle, the base is 2. The height is going to come from the right endpoint, which had an x value of 3. The next rectangle, base of 2, height comes from f of 5. And the third rectangle, base of 2, height comes from f of 7. All right, so I believe we said f of 3 was 8 previously. F of 5 was 6.66666. I don't know if we've done f of 7 yet. Let's see. 2.66666. Can we get our approximation? Oops. I got a 30 number this time. 34.6667. Okay. Over or under? Definitely. Okay. Our first rectangle was a slight overestimate, but when we start to look at the other ones, There's definitely area that we should have included, but we didn't. All right, so underestimate. All right, let's check out another one. This time we'll do a right-hand Riemann sum with 1 unit width. Still the same graph, still the same interval from 1 to 7. All right, so we'll go from 1 to 2, trace up the right side, make your dot, left down. The next one would be trace up 3, make your dot, left down. All right, 1, 2, 3, 4, 5, 6 rectangles. Area under f of x from 1 to 7 is approximately. Our first rectangle is a base of 1, and the height is going to come from the right endpoint, which had an x value of 2. The next rectangle, another base of 1. Height came from the right endpoint, which was an x value of 3. All right, so we're just going to continue the process until we get to the last one. Base of 1, height from f of 7. Is this one going to be better or worse than our previous estimate? Should be better, okay, because we have more rectangles. So if 34.6667 was an underestimate, then if this one's better, it should be more than 34.6667. Any luck? $37.6667. Yep. Over or under?
Under.
Still under. Okay, but not by much. Underestimate. Okay, if you look at the drawing, the first few rectangles were overestimates, but the last few are definitely under. And if we compare those, it looks like I have more green than I do black. So definitely underestimate. Are we getting the gist of how these work? Yeah, kind of repetitive, right? Okay, but moral of the story is we can use left endpoints to help us, right endpoints to help us. Clearly, the more rectangles we use, the more tedious it is, but the more accurate we actually are. So tonight, for a video assignment, I'd like you to check out pages 352 to 355. I know it seems like a lot of pages, but it's just kind of one example on each page. Okay, it just takes up pages. It doesn't necessarily take up time. So on those pages, you're actually going to take a look at a midpoint Riemann sum. Instead of using the left or right corners, now we're going to use the middle. And then the fourth and final one's actually going to be a trapezoid. Okay, not necessarily a rectangle. Okay, so tonight I'd like you to check out those last few pages, and then we'll do a few more examples in class. Yeah. What's that? For current numbers.
Yeah. This bro, how come you have to have 30 hours of community service?
How come?
Yeah.
That's just our standard.
It's the gold standard.